So our next thing is we have looked at the dense neural network, right? Now we are going to look at some metrics, some machine learning metrics we use to evaluate our models, right? Now I think this is what all we have been doing so far. We have been looking at something like this, right? And then this is what is known as the dense neural network. And then this is just one little part of machine learning. This is what we call supervised machine learning. So we have another form of machine learning called unsupervised machine learning. So this is supervised machine learning. So why is it called supervised machine learning? Who can tell me? This is called supervised machine learning. So why do we call it supervised machine learning? Hmm.
So what was so that one you give it the data and then you predefine the output or
What do you mean by predefined output?
no, it's like you train it with the data,
Yeah, yeah,
then you know what you are expecting as the output.
yeah, yeah,
There are two. One is supervised and unsupervised.
yeah, yeah.
Yeah, the unsupervised is that one just feed the data and then you run it to
Yeah,
according to
eh,
the
makes sense, yeah.
Are you sure?
Oh, yeah, but the terms is that in supervised machine learning, then what we do is that, as we said, we give it data, and then we give it another important metric called the label. I've been always saying a label. So we give it data in the label. So if I want to train a network to understand or to actually try to classify cats and dogs, I'll give it an image of a cat, and then I give it a label, and I tell it that this is a cat. So I'm helping the network to learn, right? So I'm helping it. So that is supervised. So you give it the data, and then you give it the label. Very, very important. But in unsupervised, you just give it data. It doesn't know what it's doing. So it has to figure it out on its own, right? So an example of the supervised one is what we have been doing, right? Classification, like they get classification, image classification, and stuff like that. You give it some kind of image and then a label. Some example of unsupervised is like probably recommendation systems on your Facebook or Instagram accounts and stuff like that, right? So now if you go there and then you keep on liking some stuff, you see that you get more recommendations from that stuff, right?
Yeah.
So that is unsupervised learning. You don't give it any kind of label. It just looks at what you are liking, and then it gives you more of that. And so all of this we have talked about this already. I said we have input layer, then some hidden layers, and then output layer and stuff like that.
Okay, in layer, what's the maximum
Hmm?
that you can get? I get in layer 3 4.
It depends on what you are doing. If you are classifying cats and dogs, so it will be two. One is for cat, one is for dog, right? If you are classifying the decades, as I said, from 0 to 9. If you are classifying decades from 0 to 100, it means that it will be 100.
100 million.
Yeah, yeah.
So
So
please, here, where does the model sit and the label sits? Where would be the label? Would the label be in the hidden layer?
oh, no, 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 no. You just give it your data as an input, and then you just say that this data is probably this kind of number or this kind of image or whatever, and then that one is always in the code. So
But
this
you have varieties of cards, so for
hmm.
this you have to get
Yeah,
different
so it
data
depends
of
on what
cards.
you are doing. So that one is your choice. It's just basically based on what you are doing. So if you are doing varieties of only cats, that is different from doing varieties of cats and varieties of dogs. Or if you are doing cats and dogs, just general cats and dogs. Everything. So everything will now make your output different, right? If you are doing some varieties of cats, probably this cat, your output changes. If you are doing only cats and dogs, then you need only two outputs, just cats and dog. But what I'm saying that everything is always in the code. This is just the network. So you write in your code that this is the data you are giving it, this is the label, and then it does everything for you easily, right?
Yes, sir.
So now we have talked about this already. I said one neuron, we have input, we have outputs. Then we have activation functions. I've talked about this formula already. right? We've talked about the activation patterns, and then the most important one is the ReLU. As I said, you give it the maximum of 0 and z, like it takes a maximum of. So if it's a negative number, it will take 0. If it's not, if it's a positive number, it maintains the positive number, right? And then we talked about in this is one example, and then this is dense neural network, right? So what we are doing is that in dense neural network, what the network or what when we are training, what it's learning is the weights and biases. That's what it is learning. It's only learning weights and biases. That's what it is doing, right? And then we talked about the optimizers and stuff like that. So now let's talk about how to create our data sets and stuff like that, right? So if I tell you to go and design a system that can classify shoes, right? What is the first step you do?
How to define what shoe is.
Yeah. So now you need as many shoes as possible. So you need to define as many shoes as possible. So once you're given an assignment like that, you have to create a data set that contains shoes, a lot of them, right? So now after you've gotten your data set of so many shoes,
This picture was taken at Taiwan.
at where?
Taiwan.
At Taiwan.
Taiwan.
So nice.
Yeah, he was there.
They have some black kids be like this.
So you train it with so many different versions of shoes, right? And then after you train, so during your training, when you gather so many images of the shoes and then you are training, right? Your system, as I said, you always measure the accuracy, and then your system always start from some kind of low accuracy. So here, your system can start from 0.92, go to 0.93, and then the highest accuracy you can get is what? 1. So that's 100% accurate. It means that it's able to classify anything you give it, or all the shoes you have given it. It's able to perfectly classify them. Right, so when you are training, that's what you'll be getting. You'll be getting accuracy close to 1. Right? Now, once you train a network with shoes like this, have you seen this kind of shoes? They are kind of sneakers, right? Now, once you train it and then you get 100%, and then you come and give it a shoe like this, your network will feel miserably. But you have designed it to classify shoes. This is what? It is a shoe, right? But it fails. And then here, it gave you 100% accuracy. But if you give it a shoe like this, then you know that you have an issue. It will fail miserably. It doesn't know what this is. Why? Because you have not trained it with this kind of shoes. Understood? So now, when you are training, you are using those kind of images to train it, and then once you are training it, the network learns those kind of images. It learns it very well. It knows that this is what you have given it, and then it learns it so much so that you can get an accuracy of 100%. But when you give it new data, you see that you have an issue. There will be a lot of issues. So that's when you have to go and now change your network again. So if you train it with all your data and then you think it's perfect, then you send it into the real world, it will feel miserable because if it has not seen that kind of data, it won't be able to classify it. Right? So now, once you do that, we say that the network has overfit. So you train it with some kind of images or with some kind of the data set. It learns this data set so much so that it only knows those ones. So it has overfit. Right? So like it's just like if you have dots here, if you have dots in x's here, and then somebody tells you this is a typical example of what we call classification. So if you have a graph like this, right? A graph like this, and somebody tells you that draw a line that separates the x from the y, right? You have this dot. Just forget about this line, this one here. If I tell you to draw a line that separates the dot and then the x, what will you do?
You will single out the y, the x from the dots.
So now you'll be tempted to do something like this. Right? Now this is what we call overfitting. Now if you do something like this, and then I place a dot somewhere again, right? And then I say, don't change your line. So are you sure that it will be able to classify that dot or the X you've added? You said because you have taken some specific kind of, you have learned, you are like, you design your thing based on only this data. So now if somebody does something, if somebody this same data, somebody does something like this, right? Somebody does a line like this, right? So now you see that with this line and then this line, right? If I'm to go to place another new data within the system, right? This here will be able to classify it better than this one.
Yeah.
But when you were drawing, this one captures everything. But you see that this one, there's a kind of error. There's an X here, an X here. But that is fine, at least. Once you give it new data, you're able to do something. But with this one, once you give it new data, it will fail miserably. And so we call it overfitting. What you want is something like this. That is the design. You get some errors, of course, but your system will be able to classify new data. But if you do something like this, your system will not be able to classify new data. It will be very difficult for you to classify new data, right? So how do we solve an issue of overfitting in machine learning? So all you do is that we talked about the validation data set, right? We talked about training data set and validation data sets. That is what the validation data set is for. So if you have a set of, if you have 100,000 images to train your network with, don't use all of them to train, right? Use 80%, so 80,000 of the images to train, and then use 20% to validate. So what you do is that you train with 80%, and then you check whether your model is training well with the validation data. So the validation data is the data that is not used for training, right? The network has never seen that data before. So while you are training, you give it another, you give it validation data to see whether it is training well. That's what the validation data set is for, right? And then again, you have to still divide, you still need another kind of data set again, called the test data. So the training data is for training, just training, right? Validation data is for validating or evaluating your model when it is training. So you are checking when it is training, you are validating, right? Now your next step is after it has finished training and validating and everything, you give it the test data. Understood? So all you do is once you are given a data set, you have to divide that data set into training data set, validation data set, and then test data set. This is very important. Understood? So now, normally, when you start, you design your network just like the one over there, right? You design a network like this, and then you use your training data to train. Once you are training with your training data, you get an increase of probably 0.99%. Once you do your testing, once you do your validation, you get 0.92, right? Once you do your test, you get 0.8. So it means that from here, you will see that you have an issue. Clearly, the training accuracy is 99%, okay, very, very high. But your test is your test is 80%. That's a very huge margin from the 99%. So what do? You have to go and change your network again, right? So you change your network, and then your network behaves like this. Your training accuracy will reduce. Sometimes it reduces, sometimes it increases. It depends. So here you are getting 0.94. Your validation accuracy is 0.93. Your test accuracy is 0.92. This is better, right? Because your test accuracy 0.92 is close to the 0.94. That is good enough. Understood? So this is how it works. So you can, and I provided another notebook for you to go and experiment it on your own.
After training the machine, after training the machine
Mm.
with the data, now along the line you realize that maybe like the sugar you just displayed,
Yeah.
maybe I'm not training with that.
Mm.
So I intend to add that as part of the data that I will use to train the machine.
Mm.
Now the already fed data, the data that you already used to train the machine.
Yeah.
Can you post training? Can you just add that one up?
Yeah,
Or you
yeah,
have
yeah.
to remove
Well,
the
now
data?
you
I just
don't have to,
add
yeah,
that. So
you can just add it
just
up.
keep adding and keep
Yeah,
training it with additional data.
yeah. That's what happens. Okay, so this is part of the code. Like, should I go through this? So like all I explain is in this code. So all you do is that the data is still on the MNext data set. So you use data to load your MNext images into TT images and test images. So you have TT images and test images, right? So now you print your TT images and then you see that there are 60,000 of them, right? And then you print your test images and then there are 10,000 of them. And then here, all you do is that you split your training images into validation images and then training images. So you split them into the training images will be 50,000, the validation images will be probably 10,000, right? And then after that, you now give it the model.fit is when is will start to train your network. You give it your training images, you give it your training labels, you give it the epoch, and then you also give it the validation data. So it will be training while validating, right? Now and then so while you are training, you'll be checking this graph to see how it is doing. Now, if you get something like this, if you are getting something like this is the blue line is your training accuracy. The yellow line is your validation accuracy. So if you get something like this, then you have an issue. Something like so it comes up and down, your validation accuracy comes up and down, you have an issue, and then that issue could be that your learning rate is too high. You remember we talked about learning rate. As I said, for the loss function, the loss must come down, right? And then you take some number of steps to come down, right? If you define the number of steps to be too small or too large, there will be an issue. So there's some kind of optimal number to use. So if you're having something like this, once you're training and then you're having something like this, you have to go and change your learning rate, right? And then you'll get something smooth like this. So now here, if you are training and then you are checking and then you are having something like this, you see that the validation, the training accuracy, when the blue line is going up, but you see that your validation accuracy is actually coming down small, like it is actually leveling up. You still have an issue, right? So they must all go up together. Understood? So all these issues, you have to go and arrange your network and add more layers, remove layers, experiment, and then get a perfect graph. Understood? And then after that, you use your test images to test it. And then most at times you will be getting an accuracy of about 0.95, right? Okay, so now let's go to another. So we have talked about accuracy, right? How to measure, and then we know how to measure the accuracy. We talked about the loss function the last time. But here we have a very, very important metric or some kind of metrics we use to evaluate our machine learning, right? So here, if I have a model like this, if I have a network that classifies cats and dogs, right? If it's a cat, then my class or my output is 1. Have you seen it? If it's a dog, then my output is what? 0. Right. So here, I've classified some kind of, I've classified some data already, and then the first one is the actual one, and then here, this is the actual classification, and then my next one is the prediction. So I've classified something, right, and then I have the actual and then the prediction. So if let's say the first one, the actual is 1, and then the prediction is 0, it means that it's a cat. The actual thing is a cat, but a predicted a what? A 0, a dog. It means that we have an issue, right? The next one is so if you see 1, so this one matches the actual must match the what? The prediction. So if I have 1, it means that it's a cat. If I have 0, it's a dog. Understood? So now we have what is known as in machine learning, we have what is known as the confusion metrics. Very important, confusion metrics, right? So, so what I do is that I've classified some data. I know what the actual thing is, and then I do some predictions, and then I know what the predicted things are, right? So I can come and draw a confusion matrix using the data on top there, and then this box here is called the confusion matrix, right? And what the confusion matrix has is the true condition is here. This one is true condition. So I have a cat. You know that cat is one, right?
Yes.
Dog is zero. So these are true conditions. Or this is the actual values, right? And then I have the what I predicted. So another one, cat here, cat is one, and then dog here. So I draw this table down. And then what I do is I look at my actual, the first one. The first actual is one, right? So the first actual is one. So the actual means that it's a cat, right? Are you listening? This is very important.
Yes.
The first one, yes, the first one, right?
Yes, sir.
It means that it's a cat. The actual is here. This is the actual value. This is the predicted value. So I come here, it's a cat. But my prediction is zero. It's a dog, right? So it means that if the actual one is a cat, the predicted one is a dog. So I come and increase, I come and put, that kind of bar there.
Tally.
Aha, yeah, whatever it's called. So I come and put one here. Then I go to the next one. My next one is the same. The actual one is a cat. It predicted the what? A dog. So I increase this one. So I do that for all, and then so if it's a cat and it predicts a cat, I'll come and do this. If it's a dog, the actual thing is a dog, it predicts a cat, I'll come here, right? If it's a dog and it predicts a dog, I'll come here, right? Understood? So in the exam, I can give you something like this and tell you to draw the confusion matrix.
Sir, can you go through it?
I don't want to draw the book. I don't want to.
Just direct it.
Nah, I mean, I don't want to draw it out because it take a long.
No,
Okay.
don't draw like this. Just explain.
Aha. So in your confusion matrix, you take your true conditions.
Yes.
The actual one will be here. So it's a cat, which is one, and then dog, right?
Which is zero.
Zero.
Then the layers are 10, right?
The what?
The layers are 10.
Nah, they are not the layers.
That's
the
okay.
predictions.
Okay, predictions. Okay.
And then I have a cat. I have this is my actual values, and then I have my predicted.
Predicted values.
Yeah. So a cat again, which is one, and I have dog,
Dog, yes,
which is what zero.
zero.
So this is what I do. Right? So I start from the first one. My actual is one. It's a cat. It predicts a what? A dog. So this is my actual. This is my prediction. So I come here. It's a cat, but it predicts a dog. So I come and put one here. The next is a cat.
Cat, yes.
It predicts a what?
A dog.
Come one here. The next is what?
A cat.
It predicts a what?
Cat.
So cat.
Oh, okay.
You understand? The next is what?
The next also a cat.
Cat. It predicts a what?
Cat.
You understand? So you go through
I think
all.
we are okay. Anybody else?
Anybody?
So how come we had a six?
Yeah. So once you do everything, then you add everything up. You know that the cat and cat. If it's a cat, the cat and cat is 6.
We have 6 predicted cats.
Understood? So we have 6. So when it's a cat, and then if it's a cat, those are 6. When it's a cat and it predicts a dog, it's 2 and stuff like that. Understood? Very, very important. Confusion matrix is very, very important.
Why did you use confusing?
And that's what it's called, confusion matrix. Right, so now, your nexus, there are some kind of definitions in the confusion matrix. So if it's a cat and then it predicts a cat, this box is what is known as the true positive. True positive. So it's a positive and then it predicts a positive, right? So a positive means a 1, negative is 0. Just take it that way. Positive is 1, negative is 0. Right? So it's a positive 1. And then it predicts a positive, right? 1. So that is a true positive. Understood? Now we have what is known as the true negative. So it's a 0. And then it predicts a 0. True negative. Now we have what is known as the false negative. It's a positive, but it predicts a negative, false negative. And then that is what in machine learning is called the type 1 error. And then we have the false positive. It's a negative, but it predicts a positive. Easy, right? False negative. That is known as the type 1 error.
So the other one.
The what?
Type 2 error. The cat is in.
Yeah, yeah,
false negative.
yeah, yeah.
I see that you are doing the video. So
What?
sake of time.
Ah,
I
okay,
see
yeah,
that
yeah.
you are doing
Oh,
a video. So
it's type 2 error, and then the false positive is a type 1 error. Understood?
Yes.
All right. So now our next thing is like so. This is how a type 1 error looks like. The type 1 error is a false positive. So you are a man, you go to the hospital, they do a test, and then they tell you are pregnant. The pregnancy test comes positive. So that is a false positive because a man cannot get pregnant, right? So that's false positive. But the test showed that you are pregnant. So.
But in this age that people are claiming to be anything, a man can get pregnant.
Go, what's that? Okay, whatever. And then if you are clearly pregnant and everything, you go to the hospital, you do the test, they say you are not pregnant, but you can see your stomach and everything is there. That is false negative. Right? So now you have something, you have some metrics called the precision and accuracy. Right? Now you can define precision and accuracy in English, right? So if you are given that thing, it's called what? It's called what daft or that or what? The one they throw the bull that So if you are given a dart, right, and then my target is the dots inside, right, and then I'm able to hit, I'm able to throw, and then about five, I do five throws, and then I'm able to hit all of them within that dart. We say that it has a high precision. You have high precision, and then you have high accuracy, right? Now, when I come here, right, the aim is to hit here, the dot. But I'm able to hit here. All of them hit here. So your accuracy is very low, but your precision is very high because the precision is how close your throws are. You'll be able to throw and then it hits one spot here. But normally, this is your target. So we say that you have high precision but very low accuracy. Right now, if you take probably this one here, the aim is here, and then you just throw it randomly. It means that you have low precision, you have low accuracy. So this definitions. Hey. So, oh, it's coming, it's coming. Oh, objectives is coming. So here we have some metrics known as the accuracy, precision, and recall, and then all of them have formulas. So the accuracy, to measure the accuracy so you'll be given a confusion matrix. Normally you are given a confusion matrix and then you ask to measure the accuracy. So the accuracy is just the true positive plus true negative all over the positive plus the positives plus the negatives. So all over the total of the images of whatever it is. Then the precision is the true positive divided by the true positive plus the false positive, right? And then we have what is called recall. It's true positive divided by true positive plus false negative. So there are these formulas you need to know and understand and stuff like that. And then we have another one known as the F1 score. So the F1 score is a way of combining the precision and then the recall. So you take two times the precision times the recall all over the precision plus the recall. That's just what is known as the F1 score. Understood? And then I gave another notebook inside there for you to go and experiment with and know how.
So that one, how do you
All the codes are in the notebook. You just click and run it, and then you see the code, and then you see the results.
Oh, in the digital.
Yeah. Yeah. Or if your Jupyter notebook don't work, use the Google Colab.
The go collab with the digital.
Yeah.
No, that machine can do. No, come on. Yeah, come
All right. So the last 10. But I gave this slides out already, so you guys should have done this long time.